So today we looking at medium problem. We're given string with letters yes or no, and that's yes means there are customer to the store. No means no customers. And we want to find the closest point that there are no improvement of the maximum customers. So for example, in this case, initial customers 0, this gives +1, this gives -1 because there's penalty, and so on. And in this case, also when we close too early, each yes becomes penalty. And we want to find the minimum close time to minimize the penalty. So the intuition is that it is a random sum when you do this last one, it increases your sum to 1. Let's make it like this. Yes, +1. No, -1. And the level is like this: 1, 0 again, 0 initial. And for example, this case, no, if you stay opened, you will have a penalty, -1. And this gives yes, so customer +1, and it became again 0. So this is kind of total number of customers, and this can't be total number of customers. So it's not just total number. It's total penalty. So when you, for example, close here, can you actually do this? I think you can, because so let's read description again. So every time shop is open and no customers, penalty goes up. And every hour shop closed and customers come, penalty goes up. So it's not that you will have a penalty or some price for closing early, but for this customer you will have penalty. It's kind of complicated to reason about why this random sum actually gives the correct answer. But when you look at these examples, you will see that the base level goes up by 2 points, then it goes down again and up, but didn't actually change. So we haven't improved the market situation. So it's like this, +2 here, and this is the same, +2. So it's not that we improve it, have any improvement in this point compared to this point. So we can keep the first one and close. So this is the reason. Now let's look at the solution. The actual code implementation is pretty much simple. You just have a running sum, like counter, and compare it to the maximum. And if maximum is new, you just put the new result. This will give you the first maximum as a result. And this is the answer. Now let's look at some other, I would think, goal fit solution of mine. So the Kotlin one. The first what I did is, let's look step by step. So you have like this goal fit intuition, and I looked at the ASCI table of N and Y, and they are exactly 11 places, one of each. So if you do this division by 10, you will have one, exactly one, if this is Y. And this is a trick of converting 0, 1 to 1 and minus 1. Now look at this max Y on this one. So I use this as search of, it's not index, it's not exactly indexes, it's the time of closing time, and it is shifted by a set of 1 of indexes. The base value is actually can be any number, so you can pick the most cool one, and the max by in Kotlin will return the first maximum value and first maximum time. This is what we search. Now let's compare it to the Rust solution, and it kind of very trickier than the Kotlin one, because max by k in Rust gives you the last maximum. I don't know why. It is maybe some performance reasons, but it is like that. And to convert it to the minimum max, you have to do this second argument. And it didn't change anything in the result, because this is just k. The k is not returned, so you can use any value. And the baseline is like most fun one. And in Rust you actually can convert a Boolean operator, Boolean value, to the integer. And this is the same trick of shifting 0, 1 into 1 minus 1. So that's it. Now time complexity is obviously of n, space complexity of 1. And that's it for today.